Physics. I'm Mr. Densmore.
Mr. Martin.
All right.
Today we're going to talk about why we do labs and experiments. I feel like students who come into physics have already gone through bio and chemistry, yet most of them don't even know why we do labs. And I think it's because nobody's ever taught you why we do labs. So we're going to focus today on how we do labs and why we do labs. And the first thing we want to look at is the fact that in physics and any science, we're looking for relationships between certain things. When we find a relationship between two objects or two physical phenomena or something, we can start to understand how they work together. And the idea of labs is to investigate to see whether or not there is a relationship.
And most of the time in physics, this year you'll see, we're going to be measuring physical quantities, be it length or time or something similar, right? We're going to go through a lot of different quantities. We're going to compare two, sometimes maybe more than two, but most of the time it'll be two quantities to find that relationship and see how they work together.
Yeah, for an example, global warming is a big thing right now, right, Mr. Densmore?
Absolutely, yeah. They said just recently it was released that July was the hottest month recorded across the globe.
And I believe it. It was hot. Now, if we were looking at global warming, for instance, there are many scientists that are doing lots of experiments right now. In fact, I've been involved in some research having to do with global warming. But if we were to look at maybe two things, trying to understand global warming more, we might do an experiment. It would have to be really large, maybe across the globe, maybe to see if there's a relationship between CO2 emissions and temperature index. And so once we did our experiment, then we could look to compare it, analyze it, and see if there actually was a relationship. And then if there is a relationship, we can start to understand how they work, or start to work towards understanding how they work. If we can't establish that there's a relationship, then we don't even know what to do about these two things. Right, Mr. Densmore?
Yeah. In the case of global warming, it's a cause and effect. A lot of people do believe that the rise in CO2 is causing the rising temperatures. There are other people who don't believe that. But that's why the data is being collected, so scientists can look at it, analyze it, and determine the relationship, if there is any, between those two factors.
Yeah, if they get all the data and they find out that CO2 emissions are rising, but temperature is falling, well then there seems to be a relationship there where if this goes up, this goes down. However, if they find that when CO2 emissions rise, temperature also rises, then they can say, oh my gosh, look at that. Looks like there's a relationship between these two things. And then by how much? If this rises a lot and this only rises a little, there's not that big of a relationship. But if this rises a lot and this rises a lot, then there is. And so the whole reason why we do labs and experiments is to look to see if there is a relationship between two things. And once we see that there is or there isn't, we can start to understand more how they work. All right, so we talked about the fact that labs are about trying to find a relationship between two things. Well, I guess we'll have to decide which two things we're trying to look at first. So the first thing that you do when you're trying to do a lab or experiment is decide which two physical phenomena or physical quantities you're going to look for a relationship for. After that, the next thing to do is to design the experiment.
So let's talk about the global warming like we were talking about before. If you were going to design an experiment to test the cause of global warming, we mentioned two quantities. We mentioned CO2 levels and we mentioned temperature. So one issue with this topic is that it's global. So you're going to be, if you really want a true experiment to look at the entire picture, you would have to expand your data collection all over the world. And there are scientists that are doing this now. Yeah. But as far as our work in the classroom, that's a little too large for us, at least right now. I mean, you know, if you move on in your studies in science, you may get into experiments that deal on a much larger scale. But for now, we're going to be toning it down, scaling it down to smaller, more compact versions of large-scale experiments.
Yeah, and then the biggest thing is that these physical quantities or phenomena that we're looking at have to be measurable. We can't look for a relationship between things that aren't measurable, like green and blue. Oh, what's the relationship between green and blue? Well, I mean, I can't really measure that. Or what's the relationship between, love and, what's another one?
Sadness.
And sadness. I mean, we can kind of like do a thing, how sad do you feel? But it's hard to measure that. In physics and most science, we like to find ways to actually measure these with numbers, length, tools, and whatever else. So these have to be measurable. And once we decide which two that we're going to choose to look for a relationship for that are measurable, we need to look at the tools we have to measure. Like a ruler and masses that have weights. Or I said that a little weird, masses that have mass, because weight is different. We'll learn that later. But these are all numbers. So this is 50 grams here,
Scales.
20 grams here. Yeah, maybe we'll get the scale.
Timers.
A timer, right. These are all things that we can measure.
All right, so when we are measuring these physical quantities, we want to make sure that the two quantities, if we're selecting two, that the two quantities are measured either at the same time or for the same trial.
Yeah, they have to coincide. We can't measure one thing and then 2 days later measure a different thing and try to connect them. It just doesn't work. Like, for example, if we're looking at distance and time for the car as it moves, we'd have to, what would we have to do?
Well, there's a number of ways to do it, but we want to try and measure the time that it takes to go a certain distance, or the distance that the car covers in a certain amount of time. All right, now both of those sound pretty similar, and either one can work. So what we'll do, how do you want to do this?
I guess I can lay it down, and if we start there, this is a meter stick. When that car goes when the front of that car goes from there to there, we know that the car has traveled 1 meter.
So we can time how long it takes to go 1 meter, and then we have a distance that the car has traveled in a certain amount of time.
Here, let's try it real quick.
Try it?
Yeah. Are you gonna?
I will.
I guess you should do it both at the same time, so that way we start.
What
I
I'm
like
going to do
that.
is start it back here.
Yeah,
Once
okay.
it gets here, I'll hit the start button.
Great idea.
Here we go. Ready? Start.
Okay. And stop.
Okay.
Nice.
So we got the time. Now we know the distance. So those are our two physical quantities that we just measured.
That happened at the same time. They happen right here. Once we went a meter, that's the time that we've got. If we wanted to measure half a meter, we'd have to take the distance and the time here. So that's what we're talking about. When we're talking about the relationship between these two measured quantities, they have to be for the same time or the same trial. We can't wait for this. We can't stop the timer here and then measure this distance. I think now that we've showed this, it makes a lot of sense. But when we first say it, it's a weird thing. We're going to show you one more example.
All right. So another example. Say we were trying to find out how much this spring would stretch when various masses were hung on it. So this would be an example of getting two sets of data from the same trial, just as we just looked at with the car. So if we have this, what is this, 50 grams.
Are you sure it's 50 grams, Mr. T?
Well, let's, to be sure, yeah, good call there, Mr. Martin. Let's put this on our scale, and lo and behold, it is 50 grams.
Okay, good. You know how
according to our scale. Yeah.
They sometimes write the number on there, but it's really not quite right.
That's a good call. So yes, it's always good to double check. Use your measurements, your tools to measure. All right. So if we hang this on the spring, we can then measure the distance that the spring is stretched. So initially, it'd probably be good to take a measurement before you put the spring on or put the mass on, and then go through, and you can run through different trials, and we can take a look. Measure from the top of the spring to the bottom of the spring. That's looking at about 3.8.
Mr. T, are you showing the students how to not measure inches?
Absolutely.
I thought so.
Absolutely. 3.75 inches. We don't measure in inches.
No.
We don't measure in inches.
This is physics.
That's right. So, let's switch that around. Here we go. About 9.5 centimeters.
Ah, standard units. I love those.
All right, so continue this. We can just put different masses on.
So that would be the two quantities we just got would be 50 grams and 12.7 centimeters, or what was it?
It was 9.5.
9.5.
9.5 centimeters.
So 50 grams and 9.5 centimeters would be the two
One
measurements for the same trial. And then if we
Correct.
change it, we'd have to take those two measurements again for a different trial. So if you put
Yeah.
another mass on here,
So we can do that.
we'd have to find out what the mass is here,
New mass.
and that would be connected to this measurement, which you're about to take.
Right. And new measurement. So we have, that was 20 grams. Of course, we would check with the scale. And the new length is about 10.2 centimeters.
Okay, so this is just what we were talking about, that any measurements we take have to be connected temporally, which means in time. So this mass at this time equates to this length here. A different mass at this time now is for this length. And so any measurements we take have to be connected in time or for the same trial. Awesome. This makes a lot of sense to me.
So when taking measurements, no matter what it is, whether it's time, whether it's length, whether it's anything, the tools that you use are very important.
Yeah.
The way that you use them are important too, and that's what we're going to talk about right now.
Yeah, there's something called uncertainty. We're going to illustrate what that is right now. Mr. T is going to show us. So I'll come over here. I'll bring the camera. Mr. T, how about you take a measurement, just like you were before, of that, oops, there we go, of the spring
All
length.
right, so we have our length of spring. We have our masses hanging from it. So I'm going to take a measurement using this meter stick. So I'm going to see what I can do here. I'm going to line that up. We have our metric scale. So that's, I'm going to say that's about 12.5 centimeters.
Okay, now how certain are you of that measurement, Mr. T?
I don't know. It's kind of hard to read.
Can you give me a percentage of how certain you are?
I mean, I'd say 50, 60%.
Okay, so you're 60% certain. Well,
Yeah.
how uncertain are you of the measurement?
I mean, that would put me 40% because I can't really tell.
Oh my gosh.
With these lines.
Yeah,
they're kind of faded and there's
40% uncertainty. That's a lot.
it's-
Why are you so uncertain?
well, just by the look of this.
Oh my gosh, look at that meter stick. That is, you can't really see any of the lines. The tool is so worn down that there's a lot of uncertainty anytime you take in a measurement. That makes sense why you'd be 40% uncertain. That's really not the best for taking some accurate data. Is there any way we can make your certainty higher or reduce your uncertainty?
Well, with this specific tool, no. But
Oh.
that's why we were saying tools themselves are important. So what we could do now, we have this set up. So we're gonna just flip this around.
Oh.
I'm actually gonna turn this over. So
Okay.
we start at 1.
Oh.
This side is
That's much nicer.
better.
Look at that.
You can
We
see each millimeter mark.
Okay.
All right.
So if you take a measurement now with this tool, what would be your certainty level, do you think?
Oh, much higher.
Can you give me a percentage?
I'd say 90%.
Okay, 90%. So how uncertain would you, 95%, so how uncertain would you be?
Maybe 5%.
See, that's so much better than 40% uncertain. So based on just the tool that you use, you can increase or decrease your uncertainty.
And for a reading here, I get about 12.1.
12.1? Okay.
I said 12.5 before. I really couldn't tell, but I feel very confident in this 12.1 centimeter.
Okay,
reading.
I see.
So-
Now, isn't there another way that, like, okay, so the tool that you use can affect how certain we are?
Yes.
What about the way we measure?
Absolutely. So if you were trying to measure the same thing,
Uh-huh.
and say you're standing back here, maybe.
Okay.
perhaps, all right.
Yeah.
And trying to get that measurement, that's really tough.
Okay.
Or another way, if you're like this,
Yeah.
okay, the top of that meter stick is, I think it's perfect. And I'm looking up at the measurement, but the angle that I'm looking at it from is not very good.
Right, so just based on the way you're measuring, your uncertainty might be less or more.
Absolutely.
So can you show me a way of measuring where your uncertainty is lower, even though your tool has a very high rating of certainty, the way you're measuring is lower?
So you want to, as best you can, get level,
Okay.
eye level, with the mark you're trying to look at. All right, so I'm going to kind of settle that down. I'm going to kind of just get down about on the same level so I can really take a look and get...
Wait. So you're showing how to measure well, except your tool is...
It's a poor tool,
Okay,
but
is
it's
there-
a good method of measurement.
Is there a way to combine those and have a very... Oh, okay,
How about
so
that?
a good tool
Yeah.
and a very certain way of measuring, rather than being back here and trying to eyeball it. If we're precise with the way we're measuring, we can also have less uncertainty. We can be more certain about the level. We can have a higher percentage of certainty. Okay,
Absolutely.
so we call that, I'm going to put this back on the tripod here. There we go. So we call that percentage of certainty versus uncertainty, we call that error. And it doesn't mean anybody did anything wrong. It's a different word, error, than in English. I mean, it's spelled the same, but in physics it means something different. It means how certain or uncertain we are. And we want to, error equates to how uncertain we are. We want our uncertainty, the level of uncertainty, the percentage, to be really low, and that's called reducing the error. We want our percentage of certainty to be really high. We want to have confidence in our measurement. So like a 95% confidence with a 5% uncertainty would be good, because that would mean our error is really low. So whenever we talk about error in physics, we're talking about how confident we are in our measurement, and that's affected by
The tools we use, the method that we use to measure.
and the method that we use to measure, right?
And those two are very important.
Yeah.
So,
Yeah, sounds good. So that it's important to figure out how, when you're designing your experiment, what tools are you going to use to have low uncertainty? What methods are you going to use to have even lower uncertainty, so that the combination of both the tool that we're using and the method we're using reduces the uncertainty to the lowest point that we could have it.
all right. So we've gotten to a point now. We've talked about why we do experiments. We've talked about quantities to choose to measure, measurable quantities. We've talked about how to measure those quantities in order to reduce uncertainty.
So I guess we figured out which two things we're going to look at.
Mm-hmm.
We've designed an experiment looking at the tools to use that will reduce our uncertainty, our error, to the lowest point that we can think of. Wait, have we done the experiment yet?
No,
No, we haven't. This is all preparation.
It's all leading up to the experiment.
Okay, so
There's
this
a lot
is
of prep work that
got
goes
it.
into these experiments.
Okay.
In order to reduce the uncertainty. That's really a main part of it. You want to go do the prep work so that your uncertainty, your error is as low as it can be.
Oh, okay.
So, but before we do the experiment, and this is what scientists all over the world do, you speak to colleagues. You consult with those around you. In your case, it'll be your classmates. It'll be us, your teachers. And we're going to do this in order to get feedback from anyone who has some feedback.
Oh, so the next step before we even get to the experiment is to talk to other people about what we were thinking?
Mm-hmm. Yeah.
But why? I'm still confused.
Well, the feedback from other people can be very important. Maybe you and your group, maybe you overlook something, or maybe there's a better way to do a measurement, or a better way to test whatever it is you're trying to test.
Oh, so I talk to other people, so that way afterwards they might say, well, have you thought about this? This sounds like a great idea, but what about this instead of that? Maybe the way you're measuring can be improved. So we're going to talk to other people so that maybe we might be able to get some even better ideas that we didn't even think of.
Right. And it might be the same the other way, too. It's a whole collaborative process.
Okay.
Maybe they weren't thinking of a way that you decided to do something, and they can say, oh, that's great.
Oh, yeah.
Maybe I'll try that.
I like that, because
So
it's all about collaboration, helping each other out.
what
Okay,
we do.
so that's the next step, is to talk to people about it.
Mhm.
And after that, I guess we'll have, after you talk to people and get the feedback, then you
finalize your plan for your experiment.
Then you got to look back and see,
back.
do you need to change anything?
Right.
And do you do the experiment?
Then I think you're good to go.
Okay.
Yeah.
So after that, you look to see, can you make it even better than you were thinking after you talk to people? And then you can do the experiment.
You can go ahead.
Okay. Well, I guess we're ready to do the experiment.
Yep.
Okay.
Yeah.
Cool. All right. So with our experiment, we're going to look for the relationship between length and mass with this spring and this mass setup. So when we hang masses here, we're going to look for the relationship between the length of the spring when we have a certain mass hanging. We've thought about how we're going to reduce our uncertainty with the measurement design. This is the design that we've come up with. We're going to hang the spring and the mass here. We're going to use this tool because it's really precise and easy to hold. It's got the same marks as the meter stick, except it's not so clumsy, so we can really, really reduce our uncertainty. We also brought the scale to double check every mass that we take. So we're not just going to say, well, it's written at 20 grams. We're going to measure, we're going to make sure that they're actually 20 grams or 10 grams or whatever it is. And we've talked to our colleagues about it. We've talked to each other about it. And we're ready to go. We've tweaked our design. Like I said, better measurement tools. We're ready to take some data. So here's the first one.
Okay.
Let's measure the mass. All right, Mr. T, I've got 111 grams.
Okay.
Okay, hang this on here. So this is for the 111 grams. Here's the length that comes with it. And the length, and then get really close so that way I reduce my uncertainty as much as possible. And I get 12.1 centimeters. Okay, so what was that? 111 grams and 12.1 centimeters?
Yes.
Oh, gosh, I am burning up. It's so high.
It's like global warming.
Woo.
I'm telling you.
Yeah. Anyway, so that's good, right? That's good enough to find a relationship. We got 111 grams and 12.1 centimeters.
I don't think I see a relationship necessarily.
Why?
It's
Because we have only 1 point?
It's only 1 point. We did it the right way. We took the same trial. We got both of our physical measurements, but with just one trial, one data point, doesn't really give us.
We can't say there's a relationship. We need a whole bunch to see what the trend
more.
is.
Yeah.
Okay, so we'll keep going.
Yeah. Data points. Do you see any kind of relationship between? We have a lot of data points here, which is good, but do you see a relationship?
I don't see any relationship. I mean,
Okay.
there's got to be a better way because this is just really. I don't know. I'm not a computer.
It's
I
a
can't
bunch of numbers.
It's a bunch of numbers.
Yeah. How can we find?
You know what? I
a
think
relationship?
there's a good way when you have this kind of data to find if there's a relationship, and that's to graph, right? Graph. All right.
Let's do it.
And it's easy to see if there's a relationship. Like if we have a straight line, that looks like a relationship to me, or a curvy line. Anything that looks like we've seen in math class, that would tell us that there's a relationship.
Right.
So, let's graph.
Let's do it.
All right, let's do it.
We have our data, which we looked at and couldn't really see any relationship.
It was so hard to see anything at all with just the mass and the length numbers.
Right, kind of jumped around. I didn't see anything that seemed to work together, to relate together. So what we did, we put it in a graph. We have our points plotted.
And it's so, I totally see some type of trend now. Like the dots almost look like they go in a line, in a straight line. Like, yeah,
pretty
it's
close.
a little
Yeah.
here and there, but that's okay because that's part of our uncertainty.
Exactly.
You know, just the tools. Like, if we had really more specific tools, like, I don't know, a laser micrometer or something, we could have more precise stuff, and the dots would be even closer together to a line. But this is so linear. It's what we call the holy grail of physics. When you're looking for a relationship and it looks like a straight line, that's what every physicist prays for. So what should we do? Connect the dots?
No.
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 No. Don't
Never
connect the dots. Okay.
No.
What should we do instead? Just
We're going to draw what we call a trend line.
a trend line. Okay.
Trend line, or
trend
a
line.
best fit line.
Best fit
You've probably
line.
heard of this maybe in math, or maybe talked about it in chemistry. Basically what we're going to do, we're going to take the ruler, we're going to fit the ruler through all of the points of data. So that...
Wait. So that every point is on the ruler?
No.
Oh, okay.
We're going to put... The line that we're going to draw is going to go through the middle,
Okay.
as best we can, of the data.
So we're going to find the happy medium.
So there'll be some dots that are on one side of the line, some dots on the other side. Some dots may be on the line, but they don't need to be. The line really needs to be in the middle of all the data to show the trend.
Okay.
All right, so let me draw that. And so it's right in there.
Nice. Wait.
Okay.
Yeah, I guess we shouldn't go through 0, 0 because that's not what the points look like. The points have a line like this, and this looks great, you know.
Yeah. So
Trend line.
we have some good data. We have a nice trend line. And now from this trend line, we can start to build the equation which will actually relate these two pieces of information that we took.
Yeah, so I guess we have established that there's some type of relationship between the mass, hanging mass, and the length of a stretched spring. And notice the title too. The title on your graph should always, 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 even if nobody knows what you did, and they just look at your graph, the title should tell them what you were measuring, what the setup was, and what you used to take the measurement. So if we look at the title, it says mass versus spring length for a suspended mass. So mass versus spring length, that's what we were looking for. Here comes the setup portion. For a suspended mass from a hanging spring. And then here comes what we use to measure. Measured with an electronic scale and a metric ruler. So that title it's a long one, and they should always be long like that. It should tell you everything you need to know.
So anyone who looks at this knows what this graph is representing.
Yeah. And now that we've established there's a relationship, we can go further to try to understand it by building an equation, or sometimes the relationship is an actual specific number. We'll find that later on, right?
Yep.
Yeah, and this is the basis for all of science. You look for a relationship. Once you establish one, then I guess you
can draw conclusions.
Make the equations, take it a step further. It's really cool, and this is why we do experiments, to look for a relationship and then use what we find to further our understanding between the two physical phenomenon that we're looking at.
And we'll do this time and again this year. So.
Yeah. All right. So just to recap the steps, step one was to look for or figure out which two physical phenomena you were going to see if there's a relationship with. So in this case, in our example, it was mass and spring length. And then what's step two?
You want to design an experiment in order to hopefully find that relationship.
Right. And we want to design the experiment taking into account the tools that we have to measure, and how are we going to measure and use those tools to reduce our uncertainty and increase our certainty with any measurement we have.
Yep.
Then
once we have the experiment designed, our own, we need to show it to other people.
Yeah, talk to
we
colleagues.
Can discuss with other people, talk to your classmates, the teacher, and get some feedback.
Yeah, maybe they can come up with some better ways, or maybe they can help us make our way, improve our design. Mm-hmm. After that, then we reassess our design. Do we need to make any changes to actually have a better experiment? And after that,
then we're ready to go.
Okay.
So we'll perform the experiment, collect our data,
look for a relationship, right? And then if there is one, like we saw with this one, there's clearly a strong linear relationship, then we can then draw conclusions, maybe build equations from that.
Right.
And we'll learn how to do that in this class.
Okay.
But this is why we do labs and experiments, to find a relationship between physical phenomena. All of science is like this. You look for relationships between physical phenomena, and then you draw conclusions from the data set that you get.
Yeah.
Cool. Anything else?
Have fun.
Here's to a great year.
Yeah, we're looking
with lots
forward
of
to
good
it.
experiments.
Good luck.
Yeah. Mr. T and Mr. Densmore signing off.
See ya.